unlocking the very secrets of nature. The U.S. science community just got its hands on an upgraded X-ray laser arsenal, one that can peer deeper, faster, and more precisely than ever before. As SLAC's LINAC Coherent Light Source, LCLS, transforms, researchers are now exploring phenomena and scientific riddles that were simply out of reach last year. Sounds revolutionary? It truly is. But here's where it gets controversial. Are we ready for the flood of data and the new frontiers it opens? At the heart of many scientific conundrums, whether it's decoding the quantum magic of superconductivity or unraveling the intricate ballet inside photosynthesis, lie interactions so minute that traditional tools just can't capture them. That's why scientists flock to the Department of Energy's SLAC National Accelerator Laboratory. The LCLS acts like a supercharged microscope, firing ultra-bright pulses of X-rays into highly specialized instruments. With this toolkit, scientists snap crystal-clear images of atoms in motion, observe chemical reactions as they happen, and probe the essential workings of living cells. Here's the big news. After more than 10 years of groundbreaking discoveries, LCLS has undergone an extensive overhaul known as LCLS-II. This upgrade increases its X-ray pulse rate from a modest 120 per second to a staggering 1 million pulses every second. Yes, you read that right. A nearly 10,000-fold leap, fundamentally reshaping what the facility is capable of. And this is the part most people miss. This jump isn't just a numbers game. It's a qualitative shift. Now scientists are revamping classic instruments and designing brand new ones to tackle questions previously thought impossible. Let's dive into the specifics. Among the new stars of the upgraded toolkit are two powerful instruments, qRIXS and chemRIXS. Both use a sophisticated method called resonant inelastic X-ray scattering, RIXS. So how does RIXS work for the uninitiated? Scientists blast samples with X-ray pulses, exciting deep-seated electrons. As those electrons shed energy released as light, researchers use that emitted light to piece together details about the material's properties. The catch? RIXS is incredibly demanding. For every billion photons sent into a sample, just one makes its way to the detector. Imagine waiting hours for a glimpse of a single photon. Georgi Dakovsky, SLAC's principal scientist for qRIXS, describes how the old LCLS setup made collecting meaningful data painfully slow. Previously, gathering just a handful of photons felt like crafting fine art. Results would trickle in over days, he explained. With the LCLS-II upgrade, things have changed dramatically. Now, experiments that once took days are completed in mere minutes or seconds. Not only is data streaming in much faster and with unprecedented clarity, but researchers can also monitor how materials change in real time, effectively creating stop-motion movies of atomic and molecular processes as they unfold. The size and capabilities of qRIXS are equally impressive. It boasts a 12-foot-long spectrometer with a swiveling head, allowing scientists to study crystalline materials from multiple perspectives at high resolution. But there's a twist. Because it requires vast quantities of X-rays, qRIXS was previously impractical. Thanks to the upgraded LCLS, it's finally making the impossible possible. Researchers are now delving into high-temperature superconductors, materials that transport electricity without any loss. Understanding the quantum underpinnings could pave the way for advances in quantum computing, better MRI machines, and, perhaps most tantalizingly, power grids that don't lose a watt. While qRIXS works best with the solid quantum materials, chemRIXS is specifically built to analyze liquids, from ultra-pure water to various solvents. chemRIXS offers a close-up on chemical pathways, such as the step-by-step mechanisms behind photosynthesis, potentially pointing us towards synthetic systems that mimic this natural marvel. Installed in 2021, chemRIXS had already been at work for years before the LCLS-II upgrade. Christian Kunis, who leads the chemRIXS team, confirmed that the explosion in photon output opened doors previously closed, enabling researchers to study dilute solutions and obtain data true to real-life conditions, something that was out of reach before. Now, shifting to the time-resolved atomic, molecular, and optical science TMO end station, another wave of innovation is underway. A standout new instrument here is the Multi-Resolution Cookie Box, MRCO. It utilizes 16 electron detectors in a circular configuration, designed to capitalize on the million-per-second X-ray pulses. By synchronizing ultra-fast laser pulses with MRCO's detectors, scientists can capture the exact moment electrons fly out of molecules and scrutinize their energy and direction with astounding accuracy. These insights are pivotal for understanding how charge and energy move across molecules at stunning speeds, a millionth of a billionth of a second. This research pushes the boundaries of quantum physics and has the potential to revolutionize catalyst development and fuel efficiency. Razib Obaid, lead scientist for MRCO, emphasizes the upgrade gave us a much broader window into the molecular world. We're no longer peeking through a keyhole. We're looking through a wide-open door. Another TMO innovation is the DREAM instrument, Dynamic Reaction Microscope, a cutting-edge tool for visualizing chemical changes in individual molecules. DREAM's powerful X-ray beam strips away electrons from a targeted molecule, leading it to explode into fragments. Scientists detect these bits and reassemble an ultra-detailed image, effectively making a molecular movie from millions of snapshots. Imagine watching photosynthesis or even DNA's response to light unfold in real time. But here's the catch. The sheer speed and repetition rate needed for DREAM to work depended entirely on the LCLS-II upgrade. In 2020, a prototype produced just a single frame in a week. Now, with the beefed-up beamline, entire reaction sequences are within reach. Past limitations have evaporated. But wait, this is the part most people don't realize. The upgrade isn't just turbocharging experiments, it's creating an avalanche of data. These vast datasets are a goldmine for artificial intelligence. Foundational AI models trained on LCLS output will enable faster material discovery and help scientists fine-tune experiments in real time. As LCLS Science Director Matthias Kling notes, AI integration is redefining the research landscape, accelerating discovery across the board. And here's where you might want to weigh in. With such rapid advances, could we be racing ahead of our ability to interpret or even manage all this data responsibly? Is AI-powered discovery an unalloyed good, or does it raise fresh ethical and practical concerns about who controls the scientific frontier? What do you think? Is the new X-ray laser toolkit ushering in a golden age for science, or are there risks we haven't yet considered? Share your thoughts, whether you agree or disagree, and let's get the discussion started.